Part 284C3M1B7C8E13C9C6D3P38D19D7b9d13a. Line 22f1fa19C3M1B7C8E13C9C6D3P38D19D7b9d13a. Cavity 2 Optomechanics 5G Wow Seti. There's the alien radio signal. This one's about the cavity optomechanics 2, algorithms, keyword research, light signals for long-distance communication device in the well data. This whole section refers to the long-distance communication stuff coming from the well data. Okay. March 23rd, 2013, keyword ideas are reflective energy, bilinear form, Fermi line, Fermi Edge Singularity. I'm going to Google the keywords Fermi Edge Singularities in the Mesoscopic X-Ray Edge Problem and Mesoscopic Fluctuations. There's the number for the data. It says Cavity Optomechanics. Keywords were Mesoscopic Fluctuations, Quantum Optics, Nonclassical Light, Glauber Sudarshan P Representation, Nonclassical Light, Cavity Optomechanics. And this is part 2. Quotes and diagrams are from Wiki. The typical model for many structures in cavity optomechanics is an optical cavity consisting of a fixed mirror with a mechanical oscillator. March 23rd, my thoughts. Looks like the obsidian mirror and laser beam formulas coming up in the WOW data. Cavity optomechanics uses a fixed mirror and a mechanical oscillator, whereas the WOW data uses a crystalline mesh lattice to diffract the electron pencil laser beam signals around the structure. Quote from Wiki, Concepts of Cavity Optomechanics. According to the quantum theory of light, every photon with wave number k carries a momentum p equals hk, with Planck's constant h and the speed of light c. This means that a photon which is reflected of a mirror surface transfers a momentum, and there's the formula, onto the mirror, since the net momentum has to be conserved. This effect is extremely small and cannot be observed on most everyday objects. However, it becomes bigger when the mass of the mirror is very small. Photons can be prepared in quantum non-classical states if one assumes that quantum mechanics also describes the physics of the motion of a small mirror. It should be possible to use quantum states of photons to create quantum states of mirrors. Compared to most typical quantum objects like photons, electrons, atoms, and small molecules, even a nanogram mirror, which can be just seen under a microscope, is larger by many orders of magnitude. This makes optomechanical structures the closest experimental neighbors to the quantum cat in Schrödinger's Gattingen experiment. Enhancing the interaction between light and matter with optical cavities, since the momentum of photons is extremely small and not enough to change the position of a suspended mirror by more than its quantum mechanical position uncertainty, one needs to enhance the interaction. One possible way to do this is by using optical cavities. If a photon is enclosed between two mirrors, one being the oscillator, the other a heavy fixed one, it will bounce off the mirrors many times and transfer its momentum every time it hits the mirrors. The number of times a photon can transfer its momentum is directly related to the finesse of the cavity, which can be improved with highly effective mirror surfaces. Another advantage of optical cavities is that the modulation of the cavity length through an oscillating mirror can directly be seen in the spectrum of the cavity. The mechanics produce red and blue sidebands around the optical resonances and shifted by the mechanical frequency. These sidebands can then be used for optical cooling of the mechanical oscillator. By detuning incoming light from resonance to the red sideband, the photons can only enter the cavity if they take phonons with energy. And there's the formula, HWM, from the mechanics. This effectively cools the device until a balance with heating mechanisms from the environment and laser noise is reached. Cavity cooling has successfully been used to cool devices to the quantum ground state. In the same fashion, it is also possible to heat structures by detuning a laser to the blue side and thereby achieving strong accelerations in the mechanical oscillator. There are several different ways of applying cavities around optomechanical structures. In the reflective case, the mechanical structure of interest is one end mirror of the cavity, or the whole cavity itself is a mechanical oscillator. In the dispersive case, a dispersive medium is brought into a cavity consisting of fixed massive mirrors. Both schemes are similar, though not entirely equivalent. A third way of achieving coupling between mechanical structures and the light field within a cavity is through evanescence fields. Cavity Optomechanics Part 3 plus the mathematical treatment will continue in our next video. Thank you for watching.